Get strong.
So before we talk about the different type of 2D materials, including graphene and 2D TMDs, so in today's lecture we will go through some basic concepts that provide some understanding how to understand the electronic property of 2D materials and also how to characterize 2D materials. Do we need to switch the light in front? Do you know how to switch out the first row light? Or just keep it like this? Or you can see this screen clearly? Okay, good. So why we need to discover new materials, right? So we know that there are different kind of age, start from the Stone Age, Bronze Age, Iron Age. This is very ancient time. So then gradually we transit to the modern age, start to develop different kind of materials, including this plastic machine and also this very famous silicon age, right, to make the electronic device. And today there are a series of new materials discovered, including the carbon and also the nanostructures, nano age, carbon age, and also you may have heard about the quantum technology. So now the quantum age, all these new technology require us to develop new kind of materials to satisfy certain applications. So the advanced electronic materials play a very important role in this in technology development. So I give you a very quick introduction about this. The evolution of this mobile phone. Right? Starting from the 1980s, we have this wireless mobile phone, which is called 大哥大, right? Very big. So you see that the size of the phone gradually decreased, right, over the years. And today, even we have the smartphones. So you see that the size in around the 1990s. See that we have this very small size phone. That's due to the invention of the lithium-ion batteries. In the past, the very bulky iPhones, because the battery is very big. If you can make the battery smaller, you basically make your phone light and size smaller and easier to carry. So now we have these smartphones we can use to access the internet that completely changed the way how we live, right? To change our habits. You know, we use the handphones even with work and take it to public transport. And also, yesterday there is a release of this foldable handphones from Huawei. Right? You may have this news online, right? So the phones gets very popular, powerful, and also foldable. Foldable, you rely on the softer materials and create a softer screen and touch screen. All these require the materials development. So to make the phones powerful and process faster, similar to our computer, right? So we need to make the computer CPU chip very powerful, which is one key element. So how to do that? So if you take your phone out, open up the back side of your phones, you take these chips out, you will find that the size of this so-called processor in your phones is very small. It's like your fingernail size, But inside this small area, it packs a lot of transistors. That's basic units for these calculations. So transistor is a semiconductor device to create the binary code. Basically, you can switch current on and off. Right? So the ability to create multiple transistors in a computer chip, you can make the calculation faster, process faster. So this is a schematic illustration of the one type of the common field effect transistor. We will go through this. You have source, you have drain, you have gate. A gate basically is a switch. You switch current flow between source and drains. So how many transistors actually packed in the process in your handphones in such fingernail size? Billions, millions? It's tens of billions. Billions. You can imagine how small each transistor you have to make. You heard about those 3 nanometer technology. That is state-of-the-art technology to make the transistor smaller, right? So that you can pack more transistors on your computer chips and handphone chips. So that's this very famous Moore's law. Basically, describes the evolution of the transistor from time involves. Right? So this empirical laws basically can predict the number of transistors packed on microchips. It doubles every 2 years. So this, it was first proposed by the Gordon Moore from this co-founder of Intel companies. So it has described the development of transistor very well, and also the power of the chips. So, but the question there always, what's the end of this Moore's law? Like how small a transistor we can make? Any new technology we need to develop if there is end of this Moore's law. But one day we cannot make the transistor beyond a certain physical limit. Right? You heard about 3 nanometer technologies, right? So that's already very, very, very small. Right? So can we make it even smaller? So that's sort of the background. The scientists in this field have tried to develop different kinds of materials to replace silicon, because in this is majorly for silicon-based transistors. So how to replace silicon is any hope. So for example, the carbon nanotubes have been proposed. Right? This is the graphene nano ribbons, right? And also this is TMD material, TMD tooling materials. And also in 2011, there is a two-dimensional MS2-based transistor that have been demonstrated that. Okay. So this, you see that the materials actually involved into layered materials, and also you make it the physical size smaller. Although this is labeled as 18 nanometers, this is a very earlier development. Right? But the good thing that if for two-dimensional materials, because atomic cylinders, right, you can make your channel materials down to atomic layer, which, for example, the carbon graphene ribbons. Right? For the silicon, it's three-dimensional bulk materials. Right? You cannot make it like a single layer of the silicon, like this sp3 type of hybridization, because it will eventually collapse. So certain kind of elements with certain bonding configuration, they can be stable as a two-dimensional materials. For example, this MS2, we have 3 layers of atoms, which is chalcogenic atoms surrounded by metal atom, right? So they can stabilize in the single layer format. So you can make it a transistor thickness down to atomic limit. And second, in principle, you can make it flexible. You can also make it flexible electronic device, and because it is softness. So there also, about 20 years ago, or even earlier, there already another concept called single atom transistor was proposed by different research groups. This is one of the device concept demonstration from the Dichalcogenides group from Australia. So basically, they have used a single atoms inside the active channel to create current on and off. This is the so-called single atom transistors. Basically, if you look at the whole structures, you count the electrodes and also this gate, the physical size is much beyond one atom size. But this active component inside the channel, the current is modulated by a single phosphorus atom, which is implanted in the surface of silicon. So this is a very nice concept demonstration. So it tells us basically if you want to use active materials in the bulk, conventional materials, right, the ability to modulate the current on or off the key component can be done to a single atoms. But of course, in terms of practical device, is much larger than that. Okay, so the 2D materials issue the promise to make this electronic device also other type of quantum device. Right? So the field starts from this isolation of the graphene by Costiano Losov and Andrew Guy from the Manchester University. The first paper was published in Science in 2004, right? So 6 years later, they received Nobel Prize. This is considered very time from the report to receive Nobel Prize is quite short, 6 years. Normally people wait many years until they still didn't win the Nobel Prize. But this field, I think, it attracts a big research attention and also in both fundamental research and also promising applications. Okay. So start from graphene, you see that a wide range of the 2D material has been developed, including this boron nitride and different type of graphene derivatives, and also these two-dimensional Dichalcogenides elements, for example, TMDs, MS2, right? So there can be semiconductor, there can be metallic, for example, NDSC2 or this TS2, right? And you basically can find all sorts of the quantum phase or the property, electronic property, in 2D field. In the conventional materials, you have the metal, you have insulator, you have semiconductor. But when you make the material down to the layered materials, to the single layer, you're still able to find these different types. Then 2D materials can offer certain property that has been discovered in three-dimensional bulk materials. But in addition, you also have some lower exotic phase, which only appear when you have the dimension reduction. You have more strong quantum confinement, right? So the behavior of these electrons in two-dimensional materials can be very different from 3D material. So, and also how many types of 2D materials can exist, right? So we can rely on the high throughput computation, right? Also nowadays we can use, we generate sufficient amount of data, we can use artificial intelligence to learning and to do some predictions. So this is one of the early work published in Nature Nanotechnologies that also has used the high throughput computation to search from more than 1,000 materials, unique, that potentially can be as a candidate for 2D. So they calculate basically the exfoliation energies. We know that in the 2D materials, to make this monolayer, you have to exfoliate, right? You exfoliate, basically you have to break the interlayer coupling. So in terms of graphite, we know that the interlayer coupling is a wonderful force interaction, right? So that is not a covalent bond, relatively weak. So you can use the Scotch tape to exfoliate, to peel the graphene, right? So this layer interaction energy determines whether material can be exfoliated in a reasonable energy input or it can be stabilized. So you look at this graph, right? So you use this carbon, we can think about it as a graphite as reference, right? We know that the graphite, if you write it using a pencil on the paper, you see that already exfoliating when you write it. So it's relatively easy and doable. You calculate this exfoliation energy, you see that many dots that have the energy above this reference, right? Some are actually below. But below one we can consider as the materials that's relatively easy to be exfoliated. But the value, the exfoliating energy, the large one means it's not doable. So it could principle as 3D stay at 3D, right? So use this kind of approach, you can predict also more than 1,000 easily exfoliable two-dimensional materials. Right. So like this material library actually is very big, so you can combine, them also can create different kind of artificial one-over heat structures. So that's one of the power of the 2D materials. So starting from this Scotch tape, right, you can get a monolayer, right? You can win Nobel Prize, right? So that's just exfoliation. By the staking, how you think about it, you have the different, you have graphene, you have semiconductor, you have metal, you have superconductor, you have the magnetic materials. All these, they offer different kind of combination. It creates, a zoo of these artificial one-over materials, just like play the Lego. So by staking, you already can do a lot. On top of that, you have another degree of freedom. You can twist the materials. By twisting, you have so-called Moray engineering. Simply you twist the graphene with different kind of angle, right? You can have this angle-dependent Moray pattern. This due to the interference effect. If you have these two types of different materials for your graphene on top of boron nitride, in addition to the twist angle, you have a lattice mismatch. This, on top of that, you contribute to modulate the large wavelength Moray patterns. So the physics like these 2D materials, one aspect is that ability to engineer these different kind of heat structures. By changing the twist angle, you can create artificial Moray patterns. Moray patterns, can have long range, large periodicity. So when you inject electrons, this can also create some very interesting quantum property, strong electron correlations, all this. So for the physics, they are very interesting to study this. One of the very famous example is this magic angle graphene, bilayer graphene. That can be superconducting. So nobody had expect until a few years ago, the carbon. Normally we create superconducting materials using the metals, using the strongly correlated materials with metal. The carbon is very light. Carbon, graphite. So when the temperature is very low, you just twist the two layers, right? You inject a little bit electron density, the materials can be superconducting in such light elements. This is definitely not expected before. So there are a lot of new interesting properties, structures we can create using the building block of the two-dimensional material, starting from graphene. Right? So there are many things to be discovered, many materials can be created, but you keep in mind, right? We can have different combination, but when you study certain structure, there must be some rationale behind why do we create this, what kind of the new property that can benefit, right? Or eventually you can have some unique combination which have a property that cannot find in this natural material. And this is the beauty of the doing this, right? You get artificial materials that can solve some bottleneck of the technology challenges. Okay, so that's some general introduction about why this field of two-dimensional materials, 2D electronic material, all this can be a very exciting platform to play with. So fundamentally, back to the conventional, some basic concept in the solid states chemistry or physics, we clarify materials with different kind of category, including metal, semiconductor, insulator, right? So metal, of course, you don't have the band gap, the conduction band, valence band overlap. So insulating, it doesn't conduct electricity very well because it has a very large gap. And the semiconductor, it has smaller gap. So the gap size determines the nature of these different categories. So the question is why the insulating materials with a large band gap, it can remain insulating, or it is considered insulating. What's the definition of insulating? for example, this woods, right? This table, it doesn't conduct electricity very well, right? Because when you apply the voltage across these two ends, there is no current flow, right? That's considered insulating material. So the reason is that this conduction and the valence band has a very large band gap. So when you apply a reasonable sized voltage, you cannot draw current to flow. The current is basically made up by electrons. Right? There are no free mobile electrons that carry. Right? So, for example, if in the semiconductor you have different sorts of strategy to create the electron carriers or hole carriers. Right? When, for example, the field band has many electrons, you can excite one electron into empty states. Then electrons become free particles, can move, propagate in the materials, right? So that is make the semiconductor can conduct electricity, right? But the insulating material, because of the large band gap, it's very hard to excite electrons into empty conduction band, right? The lack of the mobile electrons, that's why they remain insulating, right? So the question is that there are so many electrons in the field band, why they cannot move? Because there are no empty states for electron hop from one side to other side. All the seats are occupied. Nowadays, in the classroom, there are many empty seats. You can hop from different side to another side. Right? But if they're fully occupied, you cannot move. Right? You are stuck. That's the reason why electrons in the insulated, they cannot conduct electricity. So another basic concept is the Fermi level and also later the four functions. Right? So if you look at this simple band diagram, right? The bottom band, the valence band are completely filled. Right? Then the conduction band are empty. So it's similar to when you have start from the simple molecules, right? The molecules, we have the few electrons from the deep level, few, till the homos orbitals, right? Then you have this empty LUMO, right? There is a gap, homo-LUMO gap. So here you feel until you feel the top levels, then, okay, that's basically your frontier valence band maximum, right? But beyond that, then you have the empty conduction band. So then we need to define a hypothetical level, which is called Fermi level. So this is defined as at certain energy levels that this states, these energy levels, have the 50% probability being filled, being occupied by one electron at a given time. So how to define this? So this is described by the Fermi-Dirac distribution formula. So basically, if you have an energy level, which energy is here represented by E, and with respect to this hypothetical level, if this right at the Fermi level, you see that when E equals to EF, then this term will be 0, right? So then the bottom is 2. You get this 50% occupation. Right? So this is considered the energy, the state right at the Fermi energies. And if the temperature is very low, close to absolute temperature, so in this case, this Fermi-Dirac distribution function basically is a steep lines. Right? So for this, when you have the states that are above the Fermi level, that's empty. So the probability of being occupied is 0, right? But it's below Fermi energy that's filled, so you have the probability which is 1. So, but you see there are different kind of lines here. You have the red lines, you have blue lines, right? So that's actually corresponding to the situation when you change the temperature. You change basically you change the temperature, right? You increase the temperature, you see that the curve will change its shape. Basically, the distribution changes. So basically, here the red lines means when you raise the temperature. You raise the temperature, these steep lines become flatter and flatter. So this you can tell from this Fermi-Dirac equation, right? When the temperature is increased, right, the denominator is become bigger, so that make this term is not so sensitive to the energy difference with respect to the Fermi level, right? So that the change in the view gets less dramatic, right? So if you plot this Fermi-Dirac distribution with respect to the valence and connection band, right, you see this. When your temperature reaches to the absolute zero, you find that basically it's a steep. Basically, Fermi level lies in the middle between the convection band bottom and the valence band top. So, and when you have this gradual raise of temperature, you see that this distribution gets flatter and flatter. And eventually, you create non-zero probability above the convection band. This means that when you make your sample hot, make your semiconductor hot enough, you can excite so many electrons into convection band. So there will be non-zero probability. These electrons will contribute to the free carriers that can be, they conduct the electricity. Make your materials can be conductors. Okay, so in addition to Fermi level, then very often you heard about work functions. Work function is also very important that define to basically an energy barrier that you can pull electrons out of your materials. For example, the sodium potassium, right? This metal, you know that it tends to give away electrons very easily, right? They can, alkaline metals, right? They can easily give away electrons. They have very lower functions. So the energy required to pull electrons out from the nucleus is outshell electrons is very, very small. So you can use this energy difference. Different materials show different energy barrier, different work functions. Here you see that the sodium and very small, 2.4 eV. While the copper, silver, gold, platinum, they reach to 4.4 or slightly more. Also depend on this the termination of the metal. For example, you have a different kind of faces for the metal. The tungsten, it can vary slightly from 4.39 to 4.69. Depend on your facet, the crystal facet. Okay. So the work function then is measured how easily material can lose electrons and the minimum energy required to move electrons from this Fermi level to vacuum level. Okay. It depends on materials, crystal facet, and also will be modified by the surface absorbance. So the question here, when you change the crystal facet, you affect the work function. What's the reason? What's the reason? So this basically illustrates that. Imagine you have the nanoparticles, right? And nanoparticles, they have the three dimensions, right? They're terminated by different phases. Like constant nanoparticles, they can have the 1, 0, 0, 1, 1, 0. But if you look at it locally, you take electrons from certain phases, they can change quite dramatically. They change from 4.63 or 5.23. So if you use this different type of facet to facilitate charge transfer, right? between the absorbance and all these different functions matters, right? So, and also if within one particular particles, all these different phase states, they're connected, so they share the same Fermi level. But the distance between Fermi level to the vacuum level, they are different. They give you different functions here. So the question is, what has been changed that can change the function of different phases? Even the elements of the bulk is the same. Why? What's the reason? Here it is. Because of electron density telling, they can leak into the vacuum, right? You have this one, the biggest difference that there's different phase, crystal phase. The atom packing on the surface is different. The packing density is different, right? And also because of the surface termination, right? So move away from the surface, then it's break the periodicity of the atom arrangement into the vacuum, right? There's nothing inside the vacuum. That means there's the surface atoms, they have this a lot of valence electrons, right? There is no adjacent atoms to hybridize to form periodic structure. They tend to leak into the vacuum. This electron density leaking into the vacuum, it creates a surface dipole layer, right? The electron basically, is a wave particle. The density can accumulate toward the vacuum. There are nothing stopped from that, right? So they gradually leak into the vacuum. Then this side will be more slightly electron accumulated. Then the surface, very close surface layer, they are lack of the electrons. They form a positive charge, right? So this creates a surface dipole just by termination the surface, right? So you look at this surface dipole alignment. When this surface dipole, they will modify the energy barrier when you try to knock electrons from your materials, right? So if you have if this type of surface dipole has been formed, compared to a situation where your metal has a negligible dipole, so the work function in this case will be increased or decreased. So in other words, so this type of surface dipole will make it harder or easier for electrons to escape from your materials. When you have the electrons, you want to knock out from the surface, right? It makes it harder, right? Because the outer layer have the accumulation of electron density that repel electrons from escape from the surface, right? The bottom has a positive charge that drag the electrons, 2 electrons, don't leave, so eventually make harder, right? So this is will increase work functions. A different surface termination actually results different kind of magnitude of such a dipole. That's the reason why the termination make a difference that changes the surface dipole in this case. But also this is basically, all the surfaces have this kind of behavior. It's just the matter of how easily electrons density can leak into the vacuum, right? That's modified the surface work functions. But in addition to that, people working in the surface science, right? They can actually drop the molecules on the surface. So molecules, atoms, right? They can form the charge transfer between your materials. If this molecule gain electrons, they get negative charge in this case. You sort of reinforce the surface dipole, and you will increase the work function, right? But in the reverse manner, you have positive charged molecules on the surface, then you can reduce the work function, right? So you can use the absorbance of molecules to modify the work function of the materials. So instead of the work function, there are also the density of states. The solid states materials, this also matters, and very often it also relates to the electronic property of the materials. So what is density of states? Density of states is the density, right? The density of states, the state's density, the number of whatever energy levels per unit volume in energy interval, right? Just as illustrated here, for in certain energy interval, you have many energy levels, right? So then you count the number of states, the density will be high, so give you certain peaks when plotted the state's density as a function of energy, right? So if you look at the semiconductor, right? Semiconductor usually have the conduction band. This is the conduction band, CB, right? This is VB, right? They are separated by a gap. So inside the gap, there is zero energy density of states. Zero energy density of, what does that mean? So if you have the electrons, right, inside your solid, these electrons has to live in certain energy states, right? These states contribute to the density of states, right? There must be some states to host these electrons, right? But inside the gap, there are nothing. There are no density of states, zero. That basically means electrons cannot live in this energy range, right? If the electron has certain energies, potential energy, or these, in this time, they're just forbidden. Electrons cannot exist in this certain energy range, right? So there will be a gap, right? So this is empty, this is field, right? So this is similar to the molecules. Your molecule is very simple. You have the homolomer, if it's the closure, right? You have this occupy each state. They have two electrons. You occupy to the highest occupied molecular orbitals. On top of that, you have LUMO, empty, right? But here, it's simply in the sense that at each energy level, you only have two degenerate states. But in the solid, you have so many atoms that pack together. But even within a tiny energy range, you have many multiple states. So that's why they use density of states, this concept, to describe the number of states per energy interval per volume. So, okay, why this is important? Important is that for semiconductor, it can define the number of carriers at certain energies. For example, the conduction band. Why they call conduction band? Conduction band means if you are able to inject electrons into the empty conduction band, it can be mobile, right? Mobile is good, it can carry the current. In the conduction band, because there are so many empty seats, right? You only have you have 100 seats, you inject one electrons, there are so many empty, they can move around, it depends on the electric field you apply, right? But the carrier density, right? How many carriers you can inject into the conduction band, that depends on the density of states, right? Depends on the Fermi-Dirac distribution. That is the probability. So we talk about that the gap size. If the gap size is very big, it becomes insulated because the probability of occupied states in the conduction band is almost zero. The connection for semiconductor, this can be changed. When you raise the temperature, right, you create so much excited, you can use light and different kind of source to increase the probability, right? The probability times the density of states that give you this actual population of the conduction band. That is the number of the carriers. The more carriers you can inject, that can carry bigger currents, right? So this is applied to the semiconductor, right? You see that this density of states times the probability. You can create, different number of the carriers. The number of carriers will be different. So for the metals, it doesn't require such thermal excitation because the conduction and the valence band already overlap, right? There are so many states above and below the Fermi level, right? You don't have to really need a lot of energy to excite to create the electrons. and so many free electrons. When you apply the electric field, the electrons can drift and move inside the metal. Right? They can be very good conductors. So, right? That's why when you how to differentiate a metal from semiconductor. Right? This is conventional kind of you can monitor the conductivity as a function of the temperature. This is you see the metals. Right? This is the semiconductor. So for the semiconductor, when you raise the temperature, the conductivity increase, right? Now for the metal, it should opposite trend, right? But for the superconductor, the behavior is very exotic. At below certain transition temperature, the resistance drops to zero. You have infinity large conductivity. That's the reason why the metal, when you make the metal hot, the conductivity drops. For semiconductor, when you make it hot, the conductivity increase. Why? So for the metal, the carrier density is not an issue, right? There are so many free electrons. But if it becomes hot, that means the nucleus, the lattice vibration is very energetic, right? That is a bad effect that reduce the electron mobile inside the metal, so make the conductivity drop. But for the semiconductors, right? If you raise the temperature, you increase the Fermi-Dirac distribution probability, right? You target density states, you can increase the number of carrier, right? When carrier increase, they contribute to high conductivity. Right? That's the reason. For the superconductors, why they drop to have the zero resistance. The classical theory is form this Cooper pair. The Cooper pair, basically the electrons, they form sort of pairs. Right? That pairing also involves the lattice. The lattice with the positive charge, it's the coherence quantum phase. Once this Cooper pair is formed, you can transport in certain materials without resistance. Okay, so how to create carriers inside the semiconductor, because the semiconductor is one key component in making the transistor, right? Silicon, germanium, right? All these are you also can change the band gap size. It can be electronic or optical device, right? So, but the first thing is how to create the carrier. The carrier basically the charged particles can be electrons, can be holes, right? But it has to be mobile. It can be considered a carrier. Right? To mobile, you have to inject into the conduction band, right? So how to inject? You input energy, right? So when the electron, it doesn't jump into the conduction band without energy input. You input energy, you excite it. You can use thermal energy, right? Thermal, you raise the temperature, KT provides thermal energy. Thermal energy can overcome this potential energy difference. You can excite electrons into the conduction band, right? All the electrons in the valence band, they can absorb photons. Right? The photons carry energy, right? Can also cause excitation, right? So these the different ways to create excite electrons. So intrinsic semiconductor basically refers to the materials without doping, right? It contains the same number of the free bonding electrons and holes. Without doping intrinsically, right? Once you create the electrons, then you leave holes behind, right? So they have the same number, right? And this depends on temperature, right? Temperature. You raise the temperature, you can create more carrier density, right? Carriers. So these electron holes are called intrinsic concentrations. Then the number of electrons that can be created, the size through the band gap is governed by these Fermi-Dirac functions, the probabilities, and the density of states, the probability time density of state, that equals to actual number of the carriers, right? So here is a plot that's for different semiconductor, getting us a nice silicon, germanium, right? You see that the intrinsic concentration, think about the electrons concentration, when you increase the temperature, this side, right? Because this is 1 over T. So you raise the temperature, increase the concentration, right? But they show the slightly different behavior, right? But germanium, silicon, they have a much higher carrier density at the same temperature. So what's the reason? What's the reason? So this one factor is due to the variation of the band gap, right? The gap size basically associated with the bottom conduction band with respect to the Fermi level. That's the energy difference, right? E minus EF. If that gap is very big, that means in terms of this Fermi-Dirac distribution we mentioned earlier. Sorry. That E component, the value will be very big, right? That reduces the probability, right? Right? So this E, for example, this is the conduction band, this is the Fermi level, right? This is the valence band, right? The energy difference, right? If the gap is very big, this delta E is this component. If it's very big, that will reduce the value of Fe, right? So that reduces the probability. Assume that the density of states are similar, that will change the carrier concentration, right? For different types of semiconductor. Okay, so you can predict the gap size based on this kind of plot. So that will be a question we can give some time later during the break time. So that is intrinsic semiconductor. Intrinsic without doping. But the good things of that semiconductor, you can make it extrinsic. You can through doping strategy, you can increase carrier by introduce impurity or defects. So I think for all the semiconductors used in the modern technologies, you have to introduce doping. You have to introduce impurity. So that's one of the beauty of that. You don't need to be perfect always. Right? Sometimes the impurity makes the things work better. The doping is intentionally introducing impurity. You can introduce electron-rich impurity. You create n-type dopant. N-type doping. N-type doping basically you increase the electron concentration, or you can introduce p-type dopant. That means that impurities carry one less or two less valence electrons inside these, as compared to the host atoms. Right? So you have few electrons. You can create more hosts than pure host. So then you have this n-doping, p-doping, and the Fermi level in this case corresponding to a level slightly below conduction band or above the valence band, depending on the dopant. When you have the donors, you introduce a lot of donor impurity, donor atoms. You create the states that close to the conduction band. Your Fermi level will move towards conduction band. Why? The Fermi level is hypothetical level that describes the 50% of being occupied, right? Now you have the donor. The donor carry one additional electrons. You can consider as a sort of the occupied, right? Before it's ionized. Before this the electron jump into the conduction band, this donor state is occupied. Right? So that very often close to conduction band. It sort of move the Fermi level close to conduction band. So for the acceptance in the opposite manner. Right? So once these donor states, they can ionize and donate one electron into the conduction band. That creates the free carriers. Right? That's the donor. So for the silicon, how to make the n-top donors in this case? The silicon is in these columns. The silicon, and if you introduce phosphorus, the element on the right, you have one extra valence electrons. So this one extra electrons can donate into the host that become free carriers. Right? So this is the n-top dopant. But in the opposite way, if you introduce the boron, the aluminum, that's on the left side, you have one valence electron left. So this is p-top dopant. How to ionize the electrons? For example, this is the phosphorus, right? The phosphorus, how to ionize these donors? One way to think about it is, what's the difference between silicon and phosphorus? Phosphorus has one more nucleus, protons, right? Has one more electrons. You can imagine that phosphorus is equal to silicon plus one hydrogen. Hydrogen has one proton, one electron. This electron is orbital around. So imagine that this is the silicon plus one hydrogen. That's why this donor set can be described by the quasi-hydrogen model, right? So that you have the one positive charge here, you have one electron orbital around. Before ionization, these electrons is not considered as a free carrier, right? But inside the solid, this electron hole attraction force is very small. Not like hydrogen. Hydrogen atoms, right? This one valence electron, the binding energy is 13.6 eV. It's very big. The thermal energy is so small. So that electron is tightly bonding to the hydrogen atom. But here the difference is that the electron living inside solid, right? There are so many nucleus nearby that can cause a screening. That's why these electrons is loosely bonded to the impurity center. Impurity has attractive force. So you give a little bit energy, these electrons escape. So that's cause, once it escape, become free carrier, this causes ionizations. That's the way to increase the electron concentration inside the semiconductor. That's the process of ionization of dopant. Okay. So there will be a temperature-dependent carrier concentration of semiconductors. You can change the temperature. For example, it depends on the degree of temperature. You have three range. When the temperature is very low in this so-called smaller than the saturation temperature, that you basically ionize the donor states. The ionization of donor states is easier compared to ionize of the electrons from the valence. Right? The donor states is even close to the conduction band. Right? So this is the first stage. Then as you raise the temperature, right, upon certain temperature range, you already ionize all the impurities. Right, in this temperature range. all these impurities become positive charge, right? You have the free carrier even in the conduction band. So this second stage, the final one is you continue to raise the temperature level sufficient high, you start to create this intrinsic kind of excitation from the top of valence band to ionize. You can further increase the carrier density, right? So this is the intrinsic temperature excited, the 3 temperature range. Then as a result, you can plot the electron concentration as a function of temperatures. Right? They are sort of linked. So in the low temperature range, the carrier density, the electron density will increase, right? To a certain point, it will saturate. That's this point corresponding to you ionize all the dopant. Then there is carrier concentration will stay constant for certain temperature range before you heat to the high temperature regime when you create intrinsic carrier density, right? You have 3 temperature range. But if you ultra cold, close to absolute 0 temperature range, you have 0 carrier density. Right? So this is so-called freeze-up regime. Right? So you have 3 regimes: extrinsic regime, intrinsic regime, freeze-up regimes. So that is the carrier concentration, electron concentration as a function of temperature. Right? However, one important thing that we care is also this current density, the current density. The current is consisted of these electrons. Right? So it associates with the number of the carrier, that is the number of the electrons, right? That is defined by N. The second is this is a constant, electron charge, right? This is a constant. Another important factor is the carrier mobility. Carrier mobility is, you heard about the high mobility and low mobility, right? The high mobility means that the electron can propagate inside materials with less resistance, right? The high carrier density, of course, is good to reduce the energy consumption when your electrons, you travel across your material. Right? You see that on the right, if you plot the carrier density, this carrier concentration log n, you have the flat region. This region corresponding to extrinsic region, right? When you already ionize all the dopant. But if you plot the log as a function of the conductance, which is sigma equal to E times N times mu, right? Actually, this part is no longer flat. Because even your N is constant, but your mu, the mobility is not constant. Your higher temperature actually you cause lattice vibration is getting more vigorously, right? The more vibration of the nucleus, that cause higher resistance in your electrons. That make it downwards, reduced the conductivity, right? That's one of the reasons, okay? I think we take a few minutes break. After that, we continue. Okay.